Chemistry 30. We are partway through this reaction with CNA2. And we're just taking a look, and I'll just re-explain something. First question was, which side has more gas molecules reacting to product? We look at the balance numbers. That's what we're asking. 2 particles versus 1. That's why we say the product. We just went over a demonstration about how an increase in pressure would shift the reaction to the side that takes up less space. Let's say, how would an increase in pressure affect this reaction? We just arrived at the conclusion. It shifts the reaction to the left. As it's a 1 to 2 ratio, there's half as much space by those, right? So, let's kind of keep this. So more here. What happens to the amount of N2O4 and N2? Well, goes up, one goes down, they're on opposite sides, right? N2O4 increased, but the concentration, I'm going to put in square brackets. Concentration of N2O4, that means moles per liter, right? That's the side that increases. And the concentration of NO2, the chemical, decreases. If that was the case, if you increase the N2O4 and decrease the NO2, what would happen to that if I could actually do that? Brown colored, colorless. What were we thinking? Yeah. It would, we would just say less intense color. It would just fade out. The color would fade out. Less, I don't like saying less brown. Yeah. The intensity of the color would decrease or something. I don't know if that's a good word. Okay. Less color. It might even get clearer. Push color, right? Now, this part, a couple of people missing. I'm going to undo this. So let's see the opposite question. 1 particle here, 2 particles there. How would a decrease in pressure, so if I increase the volume, decrease in pressure, I'm not going to, or redo the question, but looking at this example, if I was to take this small box, get rid of it, and let it be in a larger volume, which means less pressure. What would happen? Well, now these molecules can space out, right? Now lots of space. When there's lots of space, those things collide. Collisions lead to reactions if they have enough energy, right? So, boom, this one collides with the wall, falls apart. What does it turn into? A couple of them. On, here we go. There's still a lot of space. Things are colliding. Now remember at the same time, some of these NO2s collide and form N2O4s, but at the same time, another N2O4 breaks out, right? That's once equilibrium's reached. But there's lots of space, so right now, until equilibrium's reached, these N2O4s will be colliding with each other or with the walls or with an NO2 possibly. Boom. And gone because it forms a couple of NO2s, right? You can see that that will happen again. Anyways, they're floating around, and you could form. You see what happens. More space, it'll shift to the side that can allow more particles, right? That makes sense. Now here's a reaction that you may or may not know you're familiar with. Carbonated drinks. Also in your bloodstream, that you're putting in. Ah, let's think about this. CO2. We call it carbonated because there's CO2. At home, I have one of those pop fizzers, water fizzers, soda streams. CO2 canister. And I'm adding it to the water. But let's just think about a clear, not Coke or Pepsi or something. Start your root. Sprite. Sprite at 7 hours. If you have a sealed bottle of 7 Up or Sprite, have you ever tried to squeeze a bottle before you ever open it? Can you? It's rock hard. You can squeeze a little bit, but not a lot. It's highly pressurized. This is where we love pressure. So let's first of all figure out the first question. Gas molecules only. Which side has more gas molecules? Reactant or product? Which side has the only gas molecules? Yeah, the reactant's only one. There's no gases on the right. Aqueous and aqueous. They're dissolved in water. So this is the whole thing. When I pump my soda stream thing, I'm dissolving carbon dioxide in the water. When you have a 7 Up or a Sprite, and you've never opened it yet, see inside the plastic bottle. If it's just sitting on the shelf and it hasn't been shaken or touched for the last 20 minutes, do you actually see fizz coming out of it? No, you don't. That's under high pressure. The minute you open the lid, what do you see? You see the fizz coming out. Now, that's the backwards question to number 2. I said the pressure was increased. Well, let's just think about it, because you've seen this high pressure decrease. What happens as soon as you decrease the pressure? You open up the lid of pot. It shifts this way more than that, right? Why? Decreased pressure allows the gas molecules. Okay. Now, vice versa, in the factory, when they're bottling a Pepsi factory or a Coke factory, whatever, they use increased pressure because then it shifts this way. That's why you don't see more than that. That's why you don't see CO2. You can shake it a little bit and change the system for a bit, but what happens, you will see fizz, unopened pot. So I shake it. What happens though after a minute? 2, 5. You know that you don't want to open it right there, right? You're sure. But if you wait 5 minutes, the equilibrium will be reestablished at the high pressure. You haven't changed the pressure. It'll just take a moment to reestablish. 2 minutes. When it's under high pressure, this side is clear, right? So the answer is yes. Which side would the equilibrium shift? To the right side, or you can say to the product. Now this is truly one where it is, you say products and reactants, but I mean, these are left and right. I could have easily written this just the exact opposite way around, left and right first. There is no true product or reactant. Just anything on the left we call it. Okay? What will happen to the concentrations of each substance in the equilibrium when this shift occurs? Well, the reactants decrease, products increase, right? That's why you don't see the carbon dioxide. Here's a question. You've heard this before. Coca-Cola or whatever. It's acidic, right? You've heard that? All right, just tell me if you know. Why is Pepsi acidic? Why is it? Just take a look at this. Yeah, this is the HCO3. This is the side that makes it acidic. Now, you guys don't know a lot about acids yet, but when you say H plus, that's the sign that something is acidic. Now, here's the thing. My soda stream, just pure water or whatever, carbonated water, is acidic. So it's not like if you're worried about the acidity and stuff, you think, oh, I shouldn't have Coke, I'll just have a carbonated water. You're not doing yourself any favor if you're worried about acid ingestion. Also, I know this is sometimes an elementary school sort of science project or something. Has anybody ever taken a loose tooth, like when you're in grade 3 and stuff, you're losing teeth, put it in a pop and left it for a week? Have you guys ever seen that? I have seen it. What do you think happens to the tooth over the next week or two? It decays and gets eaten away. Now, they say, don't drink pop, because it'll rot your teeth, which is true, but that's because what? Why do your teeth rot? What do we call that when you go to the dentist? Cavity, right? What causes cavities? Is it the acid or what? What do you guys know? What are you told? Why do you brush your teeth? To remove sugar. Does the sugar directly, though? Perfect. So, your teeth decay because of cavities, which are caused by bacteria that feed on the sugar. So, you brush your teeth to get rid of excess sugar so that they don't have a place to sit and lunch, right? And then dig into your teeth. Would you ever hold pop in your mouth for a week or two? Like, you know what I mean? Like that experiment that I see? No, you're not going to bathe your teeth. And in that case, it's not decaying because of bacteria and sugar, I don't believe. I think it's because of the acidity and stuff. I don't know that for a fact, so I'm not going to, I haven't done clinical trials and stuff like that. But nobody sits with pop in their mouth. It's still not good to drink pop for calorie reasons, too, as well as your teeth, like to drink it nonstop. You're nice and thin now, but I know you drink, and it's not pop, it's not acidic. You drink your iced tea, this is first grade. Anyways, but I mean, someday it might catch up to you. I used to be really skinny too, and then I stopped drinking. I stopped drinking Coke, and I was drinking Coke Zero for that reason. It's a lot of calories. Yeah. That's true. I use Sensodyne too because my enamel sucks, and I can't even now in the last 10 years. I love lemonade. I can't drink it because my teeth just ache. I don't drink a lot of citrus stuff. Who knows? All kinds of reasons. But if I knew I was going to live this long, I would have taken better care of myself.
Yeah.
I would have bet on it. How might you be able to detect if the equilibrium has shifted? Well, this year, it depends which order I choose. Grade 10, you guys, I know you guys had COVID. Did you talk about something about pH and acids? Did you guys do acids and bases in grade 10? Some years people do, some years. Okay, you did. Well, there's more. You could, we won't get into this too much, but you could measure the pH to see if it's possible. What pH does is it tells you indirectly a level of pH. It's on the water. I'm going to just say that. We won't get into it. Measure pH. Let's see concentration of H plus hydrogen ion has changed. We will talk about this then later on. So on this side, examining the following reactions predict the effect of increased pressure. High pressure, lower volume, another way of achieving higher pressure, favors the side with what? More or less gas flow? fewer particles. High pressure, fewer particles. So I take a look at this. I got 2 plus 1. I got 3 particles on the left, 2 particles on the right. So increasing pressure favors, predict the effect of increased pressure on these systems. Increased pressure shifts to the right. I'll just put I and C. Oh, this is I got to read it. Increased pressure shifts to product. Shifts. Great. The right. Product. How about the next one? How many particles on the left? B. And how many on the right? Gas. Equal. There's going to be no change because neither side, because of pressure. Now, you can argue, though. Have you ever felt a valve stem after you pumped up something or like that? Like a valve stem is the thing you attach on the tire to your compressor. Anybody? Notice anything? What happens to it as you're pumping pressure? Temperature-wise. Have you ever noticed? Okay, here's the opposite question. Have you ever bought compressed air in a little canister to blow out keyboards and stuff? What happens when you decrease the pressure, when you release pressure? It gets colder. So you could say, I'm saying no change for B because of the pressure. But when you increase pressure, you change the temperature. When you decrease pressure, you cool it. When you increase pressure, it actually heats up. So there could be a change. I didn't include energy in it. So kind of due to the increased pressure because it changes the temperature of the system. But not because you follow my reasoning here? Okay. But I'm not getting into 2 factors at once. So we'll just, when we talk these questions, isolate just 1 factor. Now the C. I see there's 1 CO and 3 H2. So 4 on the left, 1, 2 on the right. So increased pressure will shift to the right. So it's basically the same answer. I'm going to just copy. So do we have a better idea of how pressure might affect systems? Let's take a look at this. Okay. I have this reaction. And you notice it's all gases. So, and there's temperature is going to affect it. You've got a heat energy on the reactants. I'm going to, on my chart, and I advise you to do this, between heat and CH4, I'm going to just put a solid line here. Here's why. I know that if one side goes down, the other side goes up, right? So this just kind of keeps my brain in shape here. I know one side's going up, the other side is going down. Okay. I'm going to go through the written example that I typed up first. Here's what I want you to do. In italics, I have the initial change. That's this column here. Right? Change. So when H2 is raised, so here's H2, right? When it's raised, what does the system want to do? It wants to undo that change. That's the Le Chatelier's principle. We're not worried about numbers. So as soon as you see this, the initial change, just stroke through it. I want it to go back down. For this reaction, to make a reactant, something on the left side to go down, which way does it have to shift? Same logic as the other day with the left. To use up H2, goes to the right or the left? To the right. So I'm going to just put in here because this is my finger. goes more to the right than the left until equilibrium is established. Then they have equal back and forth. If that happens, does it make sense why I said then that the right-hand side, both of those things go up? And the only way to, H2 is raised, I put an arrow down on it. The only way to make that down is if heat is also lowered and the CO is lowered. Does that make sense? I've got a bunch of different ones. I'll work through one more. But I want to just mention something. Grade 10, maybe you did, maybe you didn't. A catalyst. What is a catalyst? Biology, it's called an enzyme if it's biological. What is an enzyme? What's a catalyst? Make it happen at a lower energy. For example, you've got catalysts, enzymes in your body that make some reactions that wouldn't normally happen unless they're really high temperature. Your body temperature is 37 degrees. You need some enzymes, biological catalysts. Right? Okay. Think about this. Burning sugar outside of your body. If you do that, there's a lot of energy there, right? Now you're burning sugar, but it's definitely not, your belly ain't starting on fire, right? Just, catalyst only makes the reaction speed up, but if it speeds up the forward reaction, it'll speed up the reverse reaction at the same rate. So all I want to just have on here is that there's no change for any. I just want you to be aware of it. Not a trick question. Catalysts only make equilibrium just established equilibrium, but it doesn't change the amount. Can you guys choose one of these on the chart? I don't care which one. CO raised, temp raised, CH4 raised, H2O lowered, H2 lowered. Which one do we want to do? Choose one. The pressure increased is the last row or no change. I think you guys know pressure. So choose one of the others. Sure, heat added. When heat is added, and I put in this column, temperature reading. Well, you think right away, if something's increased, what's the opposite of increased? How do you bring this back down? So my logic is to get rid of extra heat energy, temperature. Which way does the reaction shift to get rid of that? It's on the left side, so it must get rid of it. More to the right than to the left. Now, on a question like this, I could ask it a number of ways. I could say, will the reaction shift forward or reverse, left or right? Or I might just say, tell me what happens to each one of these products or reactions. I'm doing it backwards. So I only have the arrow left and right there just to kind of get my thinking. That means if it shifts more to the right, what happens to the two products, the CH4 and H2O? They're going to increase. They're going to raise. Right? Now, I'm just saving myself some error. And if that side's going up, the temperature, heat energy is reducing, it's lowering, everything else on the left side has to lower as well, right? The simplistic way of doing this, but it doesn't necessarily mean you understand. But whatever you see as a change, just say, do the opposite on that side. You follow me? When I say that, I say raise temperature, just say everything on this side will now go down. Lower. Lower. Everything on the opposite side goes up. Does that make sense? I hesitate to say that too much because it gives you the right answer, but I don't know if you understand. I really want you to think through just like those statements you had again. It shifts to the right, shifts to the left to get rid of excess, to get to increase the amount of, whatever. As a result, you'll get more products, or you'll get more. That's really how I want you to think about this. You can't do this without truly understanding. I want you to finish this chart off. Shift more to the left than to the right. I said opposite of what I wrote, didn't I? And I wrote it correctly. It has to shift more to the right than to the left. Thank you. You're right. Okay, that means the increase will happen on the right-hand side. So I'm going to just put in a raised here. Okay. So, then you were thinking right. Okay, CH4 raised. It's on the opposite side. But as soon as I see raised, I'm thinking that's the initial change. I'm throwing in a bunch of methane, CH4. Ah. Anything on, well, this CH4 is raised. How do I undo that? Which way does the reaction shift? I want to ask you that. That's important because I can ask the same setup and I can say, is the reaction shift left or right? It's really the same information. To use up something on the right-hand side, it has to go more left momentarily until you pull it down. I'm only putting that line, that arrow down over the word raise, just to get my head around it. And as soon as I do that, that means there's going to be more an increase in things on the reactant side, on the left side, right? Correct? And that'll, if the CH4 has to be decreased, the other product has to be decreased. Now, logic-wise, oh, you're so nice and polite. H2O is lower. So first thing I want you to think is, what do I do over top of this H2O lower? Arrow up or down? Low? How do we, yeah, we've lost this. So gotta bring it back up. The only way to make more water is to shift. Which way? Left or right? See people pointing. So this is making sense. To the right, more than the left, will increase the water. But if I increase the water, you can't just do that in isolation. That's the whole system. It also increases the CH4. The only way to make more water in CH4 is to use up reactant. This is momentarily until equilibrium is established. We're not worried about numbers. Two more. Hydrogen is lower. It's on the left side. Reactant. Oxygen. Well, how do we bring it up? The only way to bring it up is to shift more left than to the right. That's momentarily. Keep emphasizing. Broken right. So if we're increasing hydrogen back up, that means we have to increase everything. The last one to do on here is pressure increase. We count the particles. And what happens? Now pressure increase, there's nothing in the actual reaction that says pressure, right? That's why there's no blank already filled in. So which side does it favor? The right-hand side will increase, because it takes up the balance numbers add up to 2. Balance numbers, the CO and the 3H2O add up to 4 on the left side. Reactant's lower. We actually did this one as question C on the above. I just didn't have energy. Now this should emphasize what we took up in our lab the other day, Le Chatelier's principle. Figuring stuff out without numbers, without like we're going to do calculations quite soon. So we got equilibrium constants. This is getting mathematical. All I want to point out is, and these are made up. You know, this is like a chemical reaction. The balance, the small letters are the balance. All you do is always products over reactants, okay? Now, We're going to do an example, and then we'll talk about the worksheet. Do you notice that the balance numbers become the exponents? Okay. So right away, do this one with me here, and do this one with me right on the back sheet of the sheet. This can be your note. Write the equilibrium for this expression. I say expression of the equilibrium. So, of the reaction, from the reaction, you're writing the K value of EQ equilibrium. Now I said it's products over reactants, so the right-hand side, SO3, you put it in a square bracket as its concentration. And remember how I said the balance number, if there is one, put it as an exponent. The reactants, SO2 plus O2, well, on here it's strictly multiplying. There is no addition or subtraction within this expression. Now, I got the chemicals there, but I have to put the square on the SO2. That's the balance. Very simple. 3 more minutes. Is there any questions about that example? It's fairly easy. And then I'm going to flip the page in a second. There's 2 or 3 things to remember. Why is it 2 there? This one? The balance numbers? The balance number is. That's the expression. I'm not going to do the mathematics where I give you concentrations yet. But I mean, it's going to be your calculator and squaring and sometimes cubing things and dividing. That's it. If I only ask for the expression, that's what I'm asking for, and I'm going to ask for it throughout the rest of the course. Some questions will ask for the K value, the equilibrium constant value. That's where you get a number. Equilibrium constant expression, just that. Now, on that reaction, you'll get some practice. But don't write this up. I think this is good to just know. Classes of equilibrium, 2 broad groups. Homogeneous, homo means same as prefix, right? So this is where all the substances are in the same. These are all gases. So that's simple. That's what we just had. Heterogeneous, different, right? That means you have some liquid. Now, this is important because this is what I'm going to get rid of. You write this at the top of the page or whatever that you're using here. Only have aqueous and gaseous substances, gases, in your equilibrium expressions. You will not use L, pure liquids, or salts. I lost track of time. I thought I had another minute. We will, that's it. I'll pause and stop the record.